Module 5, Beyond Right Triangles, and Lesson 16, The Law of Sines. This lesson will allow us to take the concepts that we've been establishing here in trigonometry and start to apply them to triangles that are not right triangles. The way we will do so is by looking here at an example. On the left side here, you see a triangle that is labeled with side lengths of A, B, and C, and angle measures that are labeled as alpha, beta, and gamma. The labeling structure here is based on A being across from angle measure alpha, B being across from angle measure beta, and C being across from angle measure gamma, the first, second, and third letter in the Greek letter alphabet. To work with this triangle, we will draw a height that goes through angle measure gamma and hits at the segment A through B at point D with right angle measures, causing us to have a triangle with two right triangles inside of it. If we then try to relate sine of alpha as well as sine of beta inside of their respective right triangles, sine of alpha would be the opposite side over the hypotenuse side, or h over b. Whereas sine of beta would be its opposite side over the hypotenuse side of the right triangle that it is in. So that would be sine of beta is h over a. You notice both of these equations involve various variables, but they both involve the same variable h. If we solve both of these equations for h, the first one by multiplying b over to get h, and the second one by multiplying a over to get h, well, we get that b sine of alpha equals h and a sine of beta is equal to h, which means if they both equal h, then they equal each other by the transitive property. So we can then say that b sine of alpha is equal to a sine of beta, or if I multiply the side lengths over so that they're with their associated angle measures, in this case, I'll move A over so it's associated with alpha, and I'll do the same thing with B. Using a division, I can find sine of alpha divided by A is equal to sine of beta divided by B. Note that this no longer relates to that extra side length that we had to draw for h. This is now only relating to side lengths and angle measures that exist in that initial triangle that is not a right triangle. This will now allow us to connect these trig functions to other types of triangles using this concept called the law of sines. Note that you can do the same process drawing a different height through one of the other angle measures in order to get an association with angle measure gamma and side C as well. The same process would follow here. We have for the law of sines then, that given a triangle with angle side opposite pairs of alpha A, beta B, and gamma C, the following ratios hold. We have sine of alpha over A is equal to sine of beta over B, which is what we just showed above. And, as I said, you can do this as well with C and gamma with a different height and show that these would also equal sine of gamma over C. The law of sines is this set of three ratios, this set of three fractions that are all equal to each other. And the way that it tends to be used is by choosing any pair of them and setting them equal to each other. For example, maybe you want to use these first two because you have alpha, beta, and A, and you want to solve for one of the other side lengths, in this case B. Or maybe you want to use sine of alpha over A and set that equal to sine of gamma over C. Maybe you have gamma, A, and C, and you want to solve for alpha. As long as we have any three of these pieces, then we can solve for another. You can also consider this set of fractions for the law of sines also as A over sine of alpha, B over sine of beta, and C over sine of gamma. This note is here so you know that the law of sines is flexible, and it tends to be a little bit easier to solve for a missing side length if you start the ratios with side lengths in the numerator instead of the denominator. Now, the law of sines is going to work for a lot of cases that you will see. However, it is not magic. It is not going to work for any situation where you have some knowledge of side lengths and angle measures in a triangle. It will only work for particular cases. We have here that note the law of sines, though useful for solving values of acute, right, and obtuse triangles, will not apply to all types of triangles. To use the law of sines, one must know or be able to determine the value of an angle and its opposite side. The triangles below represent the cases where the law of sines can be used, which are the SSA case, where you have a side length, and an angle measure. The AAS case, where you have an angle measure, and then a side length. As well as the angle side angle case. That's where you have an angle, a side length in between with another angle. In these situations, the law of sines can be used because we either have an angle measure and a side across, which allows us to set up a full ratio in the law of sines, or we're able to determine one. For example, in the SSA case, we have side length A here and the angle measure across. So I can use a full ratio of sine of alpha over A and try to solve for another missing value. We can also use in the second case for angle side AAS, because again we have side length A and angle measure alpha. As long as we have a side length and the angle measure across, we can work with this. The third case may look strange because it doesn't appear that we have an angle measure and a side length that are known. The only side length we know here is B, but we should be able to solve for the angle measure across, which in this case would be beta, because we know what alpha and gamma are in a triangle that has 180 degrees. So we should also be able to use law of sines for this particular case. Note for that first triangle, though, that will cause a further complication, as that is what can be considered an ambiguous case. You will see examples of this as you go throughout Lesson 16, but what an ambiguous case means is that when we solve for our first angle measure, which in that first case, we would be solving for beta because we know alpha and A and we know B, so we can solve for beta. When we try to solve for beta, we will have to use an inverse sine function to do so. And when you use an inverse sine function for realistic angle measures, it can only provide an angle measure between 0 and 90 degrees, or 0 and pi halves. For realistic angle measures, so not counting negative angle measures. But what that means is that if the angle measure we're supposed to be calculating is supposed to be obtuse, arcsine will not be able to provide that to us directly. Therefore, in these cases that are ambiguous, it is not very clear whether the angle measure we're solving for is acute or obtuse, at least not in every case. And for many situations, we will need to consider both as possibilities. So for situations where you see SSA triangles, you may have situations where there are multiple solutions to satisfy that triangle.